Let us continue the discussion on the reciprocating engine, and we are looking at different cycles. So, primarily we are going to talk about Otto cycle and diesel cycle. So, we have looked at Otto cycle and how to calculate thermal efficiency and other parameters, and then we started off the diesel cycle, and this is what we looked at the diesel cycle thermal efficiency that we have derived. This is where we stopped, and now from here we can take it further, where we can now take it to, there could be also 2-stroke diesel engine. So, when you look at that, in a 2-stroke cycle, all the operations are exactly same as the SI cycle. So, there is but only thing that one can note here, also it is possible to have 2-stroke cycle, and this could be. Now, just to give you an idea about different these things, that applications area, the road vehicles, there are both predominant type is the diesel, and railroad locomotive, that is also predominantly use the diesel cycle. And so, essentially the CI or the diesel cycle are predominantly used in road vehicle, then rail, then marine, and stationary gas turbine unit also. But in SI or Otto cycle, that is or gasoline cycle, also airborne application, where basically is small airplanes, helicopter, this is where there is an use. Now, with that we will go to the other one, which is the supercharger or turbocharger. Supercharger or turbochargers. So, this will actually increase the, so when you use the supercharger or turbocharger, it increase the power and efficiency of an internal combustion engine through increasing the pressure and density of the inlet engine by increasing the pressure and density of the inlet air using some compressor. So, two type of compressors are used, one is the positive displacement, another is the dynamic, and there are three types of positive displacement compressor are also extensively used, like Roots, Bain, screw compressor, like that. Now, when you talk about the PV diagram of a supercharger or turbocharger, this is what it states. Then it goes like that, it goes like this, then finally comes like that, it comes and then, so this is 0, this is 1, 2, 3, 4, 5, 6, and if we put that thing and the TS diagram, so like pressure and specific volume. So, this is P naught, this is state 0, this is 1s, this is 1a. So, this is where the cylinder inlet pressure, and TS diagram. So, this is 0, this goes to 1s, this is 1a, this is cylinder inlet pressure, and this is the. So, now here we have here the boost pressure P 1 is greater than the ambient. So, the ends to get the net power will get P I is that area under the curve 1, 2, 3, 4 plus area under the curve 0, 6, 1, 5. So, the power required for driving the supercharger can be calculated considering the flow to be adiabatic steady. Now, the air when it enters the compressor at a pressure temperature like P naught, T naught, H naught, and the work supplied to the supercharger is W, and the when it leaves the supercharger the temperature pressure is P 1, H 1, T 1. So, this is at the inlet, this is at the exit. Now, from the PB diagram or the previous TS diagram, what we can write, this is H 1 minus H naught, which is Cp T 1 minus T naught, that is Cp T naught by eta s, where P 1 by P naught gamma minus 1 by 1, where eta s is the efficiency of supercharger. So, the power required to drive the supercharger then is equivalent to is m dot A Cp minus T naught m dot A Cp T naught eta s P naught by gamma minus 1 by gamma minus 1, assuming a mechanical efficiency of the supercharger and the piston is eta m. So, that is the mechanical efficiency. Then what we get, this one is m dot A Cp T naught eta s into eta m P 1 by P naught gamma minus 1. So, this is how you get the supercharger calculation. So, that is talk about this piston based engine or rather reciprocating engine. Now, we will go to the aircraft propeller or the discussion on the aircraft propeller. So, what aircraft propeller does or what it does is that it actually convert rotary motion from piston engine or turboprops to provide propulsive force, provide propulsive force. Okay. So, it may possible that, so typical impeller kind of things one can think about the propeller kind of things, that here it could be connected like that. So, this is a typical diagram of a propeller, where this is the inlet velocity of V naught. So, there are different kind of propellers, this is just an schematic. It may be fixed or variable pitch, but whatever be the case, the propeller actually accelerates a large quantity of air through a small velocity change. So, turboprop engine, so the 80 to 90% of the thrust is produced by a turbine driven by the propeller, and whether the rest 10 to 20% by the jet. And in the piston engine, the propeller produced almost 100% of the thrust force. So, it has several definitions. One can think about it is a device having a central revolving hub with rotating blades for propelling an airplane, or one can think about it is a device consisting of a set of two or more twisted airfoil shaped blades mounted around a shaft and spun to provide propulsion of a vehicle through air or water, or alternatively. So, these are actually drags the air and pushes it back to produce a lot of thrust. So, now there is a brief history of these propellers, where it was when since its invention, like it started in 3rd century BC, when the Greek scientist Archimedes figured out how to enclose a long spiral screw inside these things, and then so it started with 3rd century BC, then moved to later development around 1976, 1836, 1903, 1919 fixed pitch propellers and others into service. So, that is what the different kind of advancement 1932, 35, 45 and finally 1980, where around that time we have high speed propellers tested by NASA for propeller fans to power transport aircraft. For propeller fans to power transport aircraft. So, all along the way there are different things which are kind of tested, and now you can see this is an typical wooden propeller. So, this is fixed pitch one piece wooden propeller. So, this is used for the lighter aircraft. Then the cross section would look like slightly different, and the cross section of this blade. So, this was used for these things, and if you want to, this is a fixed, the cross section looks like this. So, this is a interesting cross section. So, that shows the hub center line, trailing edge, the blade, how the aerofoil shape looks like. So, they are typically thick, and if you see they are to provide strength. So, it is cylindrical where it fits the hub barrel, but the cylindrical portion of the shank contributes little or nothing to thrust. Some propeller blades are also designed so that the airfoil section is carried all along to the hub by means of cutoff. So, these are different kind of things. Now, if we go to the classification, and then we can see this propeller, what is the sources of power. So, one is the piston engine. So, this could be either driven by piston engine like crankshaft of a piston engine, or it could be turboprop, where the turbine shaft of a turboprop engine. So, to run this kind of propeller blades we need power, and the power comes from the either piston engines or turboprop engines like this. Now, another thing could be the material, which is important. Typically, wood was used early days, probably around World War II or something like that, but then later on the metal which are used, and after 1940 propellers are made of steel, but recent propellers are fabricated for high strength. So, high strength heat treated aluminum alloy. So, metal propeller is similar to the wood propeller, except that sections are generally thinner. Okay. So, now also there are some other designs. Now, this is another picture which can show you the cowling of these things, essentially the aerofoil shape of the propeller and how it is attached with the main aircraft wing. Then there are thin sheets and metal and other material which function like cowling as shown here. So, this will give you an idea. Now, recently these guys the material could be also composite kind of material, which are also used for fabricating this kind of blades. Okay. So, coupling to the outer shaft, so that could be another issue. Now, then we can think about control. So, there could be fixed pitch, okay, so which are used for sort of small aircraft, and blades are fixed at a certain fixed angle to the hub, usually never changes, but it can be altered on the ground only, not during flight. So, Wright brothers was the first successful developer of such kind of propellers which are fixed pitch type. Then it could be variable pitch, where these are bigger and more sophisticated planes. That means the blades may be rotated about its long axis, and this could be also again divided into two subcategories. One is the two position propeller, and another one is the adjustable pitch. Now, when you talk about two position propeller, So, the blades are limited to two angles. So, one for takeoff, another and climb, low speed operation, and the other one for cruising, which is high speed operation. Whether when you go to adjustable pitch, so where the one whose pitch can be altered by the pilot, these are controllable pitch, has automatic mechanism to adjust his own pitch to match the flying requirement. Okay. So, then we can have now constant pitch propeller. So, this is fixed pitch, variable pitch, then constant speed type propeller. These are designed to change the pitch automatically, allowing the engine always to turn over the same constant speed. So, this is another one. Then we could have feathered. So, again the turning the propeller blades so that they are edge on, making a very shallow angle to the oncoming air, minimize the air resistance and allowing the plane either to keep on flying on its remaining engine or glide to crash landing. Then could be thrust reversal. So, here the pitch of the blades can be reversed. So, a propeller makes a forward draft of the air instead of one moving backward. So, this is handy for extra braking or something. So, this is used when the typically the hand brakes and such things fails. Okay. So, what we can look at is that some fixed pitch versus variable pitch propeller. We can have like basic function like poor performance, that could be one. Then we could have fixed pitch propeller, lowest cost. Okay. So, and this side is the best performance, constant speed propeller and most expensive one. So, this is how it goes, this is how it goes, and we have fixed propeller, then we have ground adjustable propeller, we have in flight adjustable propeller. So, like this. So, from here as we move with this constant speed, we can see the performance, but at the same time this is probably the most expensive. So, this gives you an idea about this comparison of this propeller and all these. Now, the other thing would be number of propeller coupled to each engine. So, that depends on the how the design is done. So, one could be single propeller which is connected. Okay. So, the one which we have already seen, this is a single propeller kind of one, this one it is a single propeller, or we can have double contra rotating. Let us see, this is a double contra rotating propeller. this is a contra rotating propeller. So, this is Rolls-Royce Griffin powered P55 propeller. Now, these contra rotating propeller are also called, they are also called coaxial contra rotating propeller or high speed propeller. So, this apply the maximum power of an engine to drive two propeller in contra rotation, this rotation about the same axis in opposite direction. So, two propeller are arranged one behind the other and power is transferred from the engine via planetary gear or a spur gear transmission. Okay. So, that is another one. Then we have like direction of rotation, then this could be another example. Now, direction of rotation where we can have left hand propeller, like left hand propeller. A left hand propeller is one which when viewed from the cockpit rotates in the anti-clockwise direction, and when it viewed from the outside then they rotate in clockwise direction. So, this is what it is. Then the right hand propeller, that means when it is looked from the cockpit it would be rotating in the clockwise direction. Then it can rotate in the similar directions, it could be in the counter rotating directions. So, these are some of the example like counter rotating pairs. So, this is a counter rotating pair, what you can see. So, this one rotates in this direction, this one rotates in the other direction, and wing. Now, propulsion methods, there could be pusher or puller or something, then number of blades are another important. So, these are also pusher and puller. So, this is number of blades where it could be the number of blades could be 2 or 3. So, let us say number of blades that could be 2, 3, 4, 5, 4, 6, 8. So, multiple greater than 4, as example 8 bladed propeller which is shown here. So, and this one is 6 bladed propeller which you see here, and 8 bladed propeller is here. This is Hamilton Sand Strand 8 blades NP 2000 propeller. This is used in C-130 aircraft. So, there are different things which are there like its blade, its rotation, counter rotation. Now, also one important factor is that aerodynamic design of the propeller, because these are important, how to reduce drag. And so, there are the way it is done is a simple ranking Freud momentum theory. So, this is what we can use to look at the aerodynamic design. Okay. So, we will now look at some of this design, how the design of these different kind of propeller is done. like we start with some of this baseline theory and look at how the design is considered for this propeller. We will continue that discussion in the next class.